chapter 29C, and after that I will, this is mostly introducing the material, and then I'm gonna have another session to solve for problem solving. Now the next topic, it is when we have induced electric fields, and in this figure here we have a long thin solenoid that actually it is encircled by another circular conducting loop, and I will say for the solenoid it has a cross-sectional area A, and it has turns per unit length lowercase n. I will say the solenoid now is gonna have that circular loop around it, and there is a connected galvanometer that is gonna measure the current in that circular loop. If we are gonna have a current I in the solenoid and going in the direction like I can show you here, it's like, let's assume this is the direction of the current, and then I will say this current is gonna set a magnetic field B along the axis of the solenoid. We can use the right hand rule here for finding the direction of the magnetic field. Like you or your right hand, you are going to curl your fingers in all the four fingers in the direction of the current, and then the thumb is going to show you the direction of the original here. I'll call it like always the original magnetic field. Now if we are going to have, of course, if this current is steady, nothing will happen, but if we are going to have the solenoid current changing with time, the magnetic flux also will change, and the induced EMF is going to be resulting. We know that the magnetic field for this solenoid, it has can be calculated as mu zero n times I, which means mu zero, it is the 4 by 10 to the negative 7, n is the turns per unit length, and I is the current. And then if we are going to take the area to point in the same direction as B, then theta B will be BA cosine 0, and from that we can conclude that the magnetic flux of the solenoid is going to be mu 0 NIA, and when the solenoid current changes with time, this is going to be the expression mu 0 n times A here is not changing, and then it's going to be di over dt. And if the total resistance of the circular loop is R, then there is an induced current that is the EMF divided by R, and that there should be an induced electric field in the conductor caused by changing magnetic flux, and that this is the expression for it. We know that the work done by the induced EMF here is equal to the induced EMF, and therefore we can write that the integration of E dot dl equals d theta b over dt. This is valid only if the path around which the integration is really stationary, there is no motion. And E, of course, has the magnitude E, which is constant, at any point, and it can be, find it by the tangent at any. And finally, if we will evaluate what is dl here, is going to be the circumference of the circuit, which is 2 pi r. Then finally, this is the magnetic field that is going to be created in the circular loop. Now, eddy currents are really when we have a piece of metal moves through a magnetic field or located in a changing magnetic fields, we're going to have electric current induced, and we call these eddy currents. Conductor detectors used at the airport checkpoints are really operate by detecting the eddy currents induced in metallic objects. I want to show you the demo here from the textbook. Just 1 second. And okay, the eddy currents demo is just to show you how really the different metals, they are going to respond with different
In this demonstration, I have 3 metal rods, a brass rod, an aluminum rod, and a copper rod. I also have 3 strong ring magnets, which can move freely along the rods. Now, each rod is not magnetic in any way. So what I'm going to do is I'm going to bring all 3 magnets up to the top and let them go at the same time. The question is, which magnet will reach the bottom first? Will the magnet on the brass rod reach the bottom first, on the aluminum rod, the copper rod, or will they all reach the bottom at the same time? So as you can see, the magnet on the brass rod made it to the bottom first, and then the aluminum rod, and lastly, the copper rod. This is due to eddy currents being set up in each rod by the magnet, and eddy currents also depend on the conductivity of the rod. Copper has the highest conductivity of the 3 metals. Next comes aluminum, and finally brass. So that was the order in which the magnets finished: brass, aluminum, and copper.
Okay, then this is really talking about eddy currents. Now, also we have an idea, we have another maybe type of current we're going to look at, which is called displacement currents. And really Ampere's law is incomplete, the one that we introduced before. And I will say in order for maybe to make a correction, we need to say then when we have a capacitor that is charging, the electric field is increasing between, of course, the 2 plates. We can define also another current called displacement current, ID in the region between the plates, and this is really the one that is regarded to be the source of the magnetic field between the plates. And that displacement current can be calculated as epsilon times d phi electric divided by dt. Then the time rate of change of electric field through the area divided by time is gonna has to do with the displacement currents. Okay, finally, Maxwell equations of electromagnetism, all the relationships between electric and magnetic fields and their sources are summarized in these 4 equations. These are really very important. The first Maxwell equation, it is Gauss's law, where it's saying that the integration over an enclosed surface E dot dA equals Q enclosed divided by epsilon 0. And the second, it is from chapter 27, the same very like it is Gauss's law for magnetic, and that is when we integrate over a closed area for B dot dl is going to give us 0. And of course this is because the nature of the 2 fields are really different. The third Maxwell is the chapter's formulation of Faraday's law, which is integration closed over a closed surface of E dot dl equals negative the change in flux over time, d phi b over dt. The fourth, it is Ampere's law, but with the correction adding displacement currents. And then it is saying that the integration of B dot dl over a closed surface should equal mu zero, which is the magnetic constant, multiplied by IC, which is this displacement, the conduction current, and then the displacement current through the bath. Now, if we have empty space, which means we don't have any charges, so the fluxes of E and B through any closed surface, they should be equal 0. And in empty space also, there is no conduction currents, so the line integrals of E and B around any closed bath are really related to the rate of change of the flux of the other field. And the last thing we're going to talk about, it is superconductivity in a magnetic field. There are some materials when they are really below a critical temperature Tc, they are losing all their electrical resistance, and they will behave in a way that they're going to expel any magnetic field. This is called Messier effect. And when we place the superconducting material in a uniform applied magnetic field, and then lower the temperature to a certain temperature, then all the magnetic flux is going to be expelled from the conductor. This is a very, like a kind of promising technology. And I want to share with you the video here for superconductors. And this is the last thing that we are going to do here with this chapter. But then we have the remaining, where did I save that? It should be here, yes.
Means that any superconductor will expel magnetic fields if you... This episode was made possible by the Vsauce 3 Patreon. To support Vsauce 3 and get early access to videos, wallpapers, live hangouts, and more, sign up at patreon.com/Vsauce3. I love you.
Let me check if this is... Yeah, this
means that any superconductor will expel magnetic fields. This episode was made possible by the Vsauce 3 Vsauce. I'm Jake, and nitrogen is a gas until it gets really cold. Then it turns into this. Liquid. In this state, it has a temperature around minus 196 degrees Celsius. And these drops that are shooting off trailing vapor, well, they're literally boiling away into nitrogen gas at room temperature. And because nitrogen has a high evaporation expansion ratio, each drop expands to 700 times its volume in gas, even though it was just a tiny drop. Using a thermal camera, we can see just how drastic the temperature change is. Once our container is filled with liquid nitrogen, it entirely becomes this deep blue. You can even see the liquid nitrogen boiling away on the surface. Whereas in real life, or with a regular camera, we can't see through the gas at all. But we are here to levitate an object, so what does liquid nitrogen have to do with magnetic levitation? Because you can make magnets levitate without it right now. And to demonstrate this, I'm going to use Ink's Levitating Rings, which is a fun product that Michael, Kevin, and I made for the Curiosity Box. There's a link down there in the store if you want to get your own, or you can use any two magnets that you have at home. Now, let me show you how this works. If these two magnets have like poles facing each other, they repel each other. It is the same principle for how maglev trains work. And the opposite occurs if we flip the magnets around. They're attracted to each other. But what we're doing here is not regular magnetic levitation or maglev. It's superconducting maglev, which is different. First of all, let's discuss superconductors. A superconductor is a material that exhibits two incredible properties when it is cooled below a so-called critical temperature. The first is that they have zero electrical resistance, but more important for our purposes is the Meissner effect, which causes a superconductor to completely expel magnetic fields when they enter their superconducting state. What that means is that a superconducting material will actually levitate over a magnet, even though the material itself is not magnetic. Now, this is our superconductor, a small disk made of yttrium, barium, copper oxide. Actually, in this whole thing, the superconducting material is just a tiny sliver of crystal grown on top of a stainless steel core and covered by a protective layer of silver and aluminum. And when I say a tiny sliver, it really is. It's just 3 microns thick, 30 times smaller than the thickness of a human hair. And if I were to put a magnet next to it, well, nothing happens because it will only levitate when it's below that critical temperature, which is why I drowned it in liquid nitrogen. One of the most amazing things about superconducting levitation is what you see here. Not only does the disk hover above the track, but it can hover below it as well. In fact, we can shape the track any way we want, and the disk zooms along at exactly the same height, no matter its orientation, with no friction or resistance. That's due to a phenomenon called flux pinning or quantum locking. Basically, while the Meissner effect means that any superconductor will expel magnetic fields, if you intentionally introduce some imperfections into that material, then a little bit of the field can penetrate it in discrete quantities called flux tubes. Inside each of the tubes, essentially a tiny bit of magnetic field gets trapped inside the superconductor, pinning it in place. And what I mean by that is that our superconductor, our disk, is quantum locked to the magnetic field generated by this track. That's what allows our disk.
I will also leave for you that video to watch if you like, and I will say this concludes chapter 29 material, and then we're gonna have another session for the problem solving. Thank you very much for listening, and see you again.